All right, we dive into chapter 18, which actually is more of the same, but, well, let's just get started. Here's the outline as I see it. This mini lecture will cover parts 1 and 2, which is basically the introductory stuff. The next mini lecture I hope will cover oxygen and nitrogen, and the third will all be about the aldol, and there will be several subsections to that. So that the aldol is kind of the big thing in this chapter, but this first part's not trivial. So let's just dive in. It's a continuation of chapter 17 in that CO is still the hard electrophile, but we have some new nucleophiles. Now we're looking at heteroatoms: oxygen, nitrogen, sulfur, phosphorus, and a couple of carbon nucleophiles. The cyanide anion is a weak nucleophile, as is the enolate. So this chapter is the nucleophiles are a lot different this chapter in that they're the soft, weaker nucleophiles that will react with the CO double bond. The part that's a little sneaky is they sneak in two new reactions that are tangentially related. We're going to learn all about hydrolysis in this chapter and a new reduction reaction, because when it comes right down to it, in terms of reduction of a carbonyl, well, we've learned how to go from oxidation state +2 to oxidation state 0, but we don't yet know how to go all the way down so that the carbon is fully reduced by adding 2 hydrogens, which would make this -2. So we'll be learning a new reaction that allows us to do that in this chapter. It's going to seem like a lot of stuff, but you know what I'm going to say. If you focus on the mechanism, it is all tied together by nucleophiles and electrophiles. So, important thing to start off with is the concept of acid and base catalysis. When we were looking at these hard nucleophiles in chapter 17, you could not possibly be under anything but basic conditions, because if you had any protic solvent or proton source at all, you would react with any of these reagents and quench them. You had to wait until the addition to the carbonyl was complete, and then you can add your acid workup. Now, these nucleophiles are sufficiently weak that we can actually have acid or base catalysis. So we can put the acid or the base in the beaker, that's what it means by in situ, in the beaker or flask at the same time as the carbonyl and the nucleophile, and that will enhance the rate of reaction. So, a key point of this acid-base catalysis stuff is that acid-base always wins. Well, that's, we've heard that 1,000 times already. But what does it mean? In concrete terms, it means if we're talking about acid catalysis, the very first step in the mechanism is invariably going to be protonation of the carbonyl. So you'll always draw that first step to get that that cationic intermediate, your protonated carbonyl. Hey, this looks a lot like solubility testing, as I recall. So that is the first step of the mechanism under acid conditions. Why? Well, when you protonate that carbonyl, you've dramatically strengthened the electrophilicity of the carbonyl carbon. So we know this is an electrophilic carbon to begin with, but when we look at this resonance contributor, it's really obvious that that is electrophilic. So that when we add our nucleophile, in this case methanol, the whole reaction is facilitated by the presence of that enhanced positive charge on the carbonyl carbon, and you get a faster reaction to give this intermediate. Under basic conditions, well, again, the rate of reaction is enhanced. Why? Because in this case, of course, the nucleophile is stronger. So here I've got a weak nucleophile, just a plain old neutral oxygen, but a strong, much stronger electrophile. Under basic conditions, I've got a moderate electrophile, because we just have a delta positive here, but not a full-fledged positive charge. But I have a much stronger nucleophile. So in either case, the reaction rate is enhanced by catalysis. Lots of take-home messages, though, as you work through the mechanisms in this chapter. First, you're always going to have to think, am I under acidic conditions or am I under basic conditions? You're going to have to pay careful attention to formal charges. And you should think about the relative energy levels of the species involved, as shown in figure 18.1. That basically this is all about energies and the relative energy levels of species, and figure 18.1 does a dynamite job of pulling this all together in an energy diagram. Alright, so an example of this introductory stuff is the cyanide anion versus HCN. So it's very typical to think of HCN as a pretty good acid, so that it would ionize in the presence of water to give you the cyanide anion and H3O+. But you can see from these pKa data that that's really not going to happen to any appreciable extent. It's a very weak acid. So when it comes to actually trying to protonate the carbonyl to make this a stronger electrophile and this a stronger nucleophile, not so much. This is definitely an unfavored reaction, an unfavored acid-base equilibrium. So for this addition of Cn- to react at the carbonyl carbon and get addition to the polar pi bond, you have to have basic conditions. You must catalyze it with a base to make that work. So what does this really mean? Well, if I catalyze it with a base, surely what that means is that I would just add some strong enough base that could deprotonate this and give me my Cn-. But the thing is, we're going to do that simply enough just by adding the conjugate base that's already formed. So it's a piece of cake. I can pour in the salt in the presence of HCN, just a catalytic amount of potassium cyanide in water, and I'll get this is called the cyanohydrin. So just to run through the mechanism, we're under basic conditions. So I can't protonate the carbonyl. There's no significant proton source around. Addition to the carbonyl kicks the pi electrons up on the oxygen, giving me the oxyanion. Note that this is a reversible reaction, but in the presence of these conditions, we should be able to not do that. Look at this acid-base equilibrium and compare this conjugate base to this conjugate base, or this conjugate acid to this conjugate acid. And the weaker acid-base pair is formed as usual. Check the pKa values. So that's just one example of how you're going to run through the mechanism. You're just going to think about what your conjugate acids and conjugate bases are. It would never be a bad idea to review the acid-base chapter, because you're going to be doing a lot of proton transfer in this chapter and the rest of the semester. Alright, now notes about this particular nucleophile and other weak the weak nucleophiles we'll see in this chapter. The cyano nucleophile is a soft nucleophile, so remember that it is going to act at the electrophilic beta carbon of a conjugated system. Okay, so soft gives me that intermediate. The end product, of course, shows not a cyanohydrin, not addition 1,2 as we saw in the previous slide, but addition at the beta carbon and disappearance of the double bond. So stand forewarned that on page 868 it explains that you get to this ketone from tautomerization of the enolate to the ketone. They just say tautomerization. But I'm going to expect you to show the mechanism, and that mechanism is very straightforward. Yeah, you know what? That's not appropriate. We got to show it and see like so. So all you need to do is push your lone pair negative charge down and protonate with whatever acid is present. Should think about which one that would be. Would it be the HCN or the H2O? And thereby you get your ketone. So it's not a big deal, but don't think that you can just say tautomerization when I'm asking for a mechanism. Okay, so here's a little practice problem for you. At this stage of the game, at the beginning part of chapter 18, you now know how to go from cyclopentanone to A, B, C, D, and E. All of these random reactions, addition of H-, addition of bromine, KCN now, sodium hydride, followed by ethyl chloride, etc. This is a good practice problem for you to work on. Coming next, the wild, wacky world of oxygen nucleophiles, but unfortunately someone gave me the feedback that they would really like more jokes at the end of these mini lectures, and you may live to regret this. This is a knock-knock joke. Knock knock. Who's there? Grace. Grace who? Gray skies are gonna clear up, put on a happy face. Oh, I think I really botched that. Oh, that's right, it's gray skies are gonna clear up, put on a happy face. Oh, geez, enough already. Okay, like I said, you may live to regret this, and we will wrap this up and get on to the next exciting mini lecture.